past for the what we call the most famous quantum algorithms that that work only on like perfect quantum computers that we call fault-tolerant quantum computers. Basically, these computers, we don't have them yet. What we have is noisy intermediate scale quantum computers. For this type of computers, we've been using variational algorithms that seems more resistant to noise. So in this last workshop, what we're gonna do is we're gonna be using variational algorithms, the ones that we looked at the last time, specifically for machine learning problems. But first, okay, so the outline is gonna be just, I'm gonna give you a small introduction. I'm gonna present you the problem. The problem we're gonna be looking at is gonna be binary classification. Then I'm going to tell you a little bit what's classification in machine learning in general. A little refresher on the quantum things that we've been looking at in the last couple of weeks. Then I'm going to go straight ahead into what we do, how we can do machine learning with the quantum computer. So first, how to load the data. This is called data embedding in quantum feature space. And then how do we classify this data once it is in a quantum state? So this is what we call a quantum measurement and how we construct with that quantum classifier. And at the last part, we're going to look at how you train a quantum classifier. But first, and this is the most important thing, it's today quantum machine learning does not work. So this means that quantum computers will not solve your data problems anytime soon. Not this year, not in the next 5 or 10 years, unless we do something. And if deep learning already solves your problem, this is going to be the best that you're going to get. So deep learning is way, way better than quantum machine learning. So once that's said, there are things that we can do. I'm going to show you how we can do it. On this small example, so this is called the iris dataset. The dataset is basically, we have measurements of flowers. We have 3 different classes, and these are like 150 flowers that were measured. And let me tell you how you do it. So you have 4 different measures on each flower. You have the petal length. This corresponds to the first element on each one of the vectors. Each vector X is going to represent a flower. It has 4 different measurements. So it has the petal length. The next one is the petal width. Then you have the sepal length and the sepal width. Okay, and we're trying to like characterize each type of flower based on these 4 measurements. And we have 3 different classes, 3 different types of flowers: the setosa, versicolor, and the virginica. But what we're gonna do is we're gonna do binary classification. So from those 3 classes, we're gonna choose 2. So this data set, what we call the domain set, comes from 4-dimensional vectors that have this type of measurements from the flowers. The labels, we're gonna focus on only 2 classes. So we're gonna forget 50 of these flowers. We're gonna end up with just 100 samples. And we only have 2 classes, so we label them by either by colors or by one is a 0 and the other one is the class 1. And there's the assumption is that there is a labeling function, so that you give it the measurements of a flower and it tells you which flower it is with 100% accuracy all the time. And the goal is to learn this function. So try to create a function that is built on a quantum computer that allows us to classify this data set. So in supervised learning, what we have is we not only have the data, but we have labeled data. What that means is that for each flower, we know the type of the flower. And now we look at the whole domain of all possible measurements of flowers. So this is the domain set that we call. Now, from there, we're going to get a subset that we call the train set. And this is just a finite sequence of pairs. We're going to have like from the 100 that we ended up when we ditched the other 50. We're going to take like around 80 for the training set. And then independently from the training set, we're going to have a test set. So the other 20 flowers that that we lack or that are still there, we're going to call it the test set. So, and the idea is that we want to build a classifier. So a classifier is receives an instance of the domain set, so a 4-dimensional vector, and will give us a label. So it's going to be either the label 0 or label 1. And we have an algorithm that is called the learner or the learning algorithm. It's basically an optimization algorithm that receives the training data and an instance of a classifier that could or could not work. And it will output an optimized classifier that should have a better performance than the initial one. And we can measure the error of a classifier by looking at how the proportion of errors that it makes on the data set. And the goal is to find a classifier HT that minimizes this error. Okay. So yeah, the objective will be to take the input data and to learn an HT that is built on a quantum computer. So the classifier is going to be built on a quantum circuit, and we need to find a way to train it. Okay, so let's go back to qubits. Now, when we have a qubit in superposition, remember that we can write it down on the Dirac notation with the alpha ket0 plus beta ket1. And the alpha and the beta, when we take the modulus and we square it, that gives us the probabilities of measuring 0. And for beta, that gives us the probability of measuring state 1. Now, we can represent states on something that we call a block sphere, but this works only for 1 qubit. Okay, so this will give us a visualization of what happens at the 1 qubit level. So for example, the state 0 is going to be represented. So we have like a unitary sphere. So all the vectors on the surface of the sphere have a norm equal to 1. And the vectors will point to the surface of this sphere. And we're going to label the north pole as the state 0 and the south pole as the state 1. So for example, in this case, if we want to represent the state 0, it will be an arrow pointing to the north pole. If we have the state 1, this will be an arrow pointing to the south pole. And if we have a linear combination or a superposition of states, this will be like in the middle, like in the middle of the way between the 0 and the 1. But it has like an angle, so it's not and this angle depends on the state of the qubit. So I'm gonna get into the details of this later. But if you ask, for example, when you change the sign of the one state, this will be reflected to the other way. So there's a way to represent all the states of the qubits there up to something that we call a global phase. But I'm not gonna get into this because it's not gonna be important. But so the important thing is that we can visualize quantum states in the block sphere. And in the block sphere is where we're going to send our data. So this gives us like a way to visualize what's happening to the data when we put it into a quantum circuit. So, and we remember some of the gates. We have the X gate, the H gate, and the C gate. We have the formulas here. I don't think we're going to use them today, so it doesn't really matter. And you already know some of them. Yeah, so this is... So we have other type of gates that I've been telling you about. We have the formulas for them. And basically what they represent, these are rotations around certain axes. So we have rotations around the x-axis. And so you can see here the x-axis is like the one that starts with an X on the block sphere. So if you have a vector that points all the way to the north and you rotate by an angle, you will rotate along the x-axis. So as you can see here, this vector is like rotating in this way there. Now, if you rotate along the y-axis, the same vector, it will rotate along this way. Okay. And this will be, so if you rotate by this angle by pi, you will land exactly here, which will give us the superposition that we know with when we apply the Hadamard gate. So, and the same thing for the C. So for the C, you will have rotations along the C axis, which is the vertical axis. Okay, so for 2 qubits, we know the same thing. We have the direct notation for this. I think we all remember the C0, so it's a control operation. Really don't think we're gonna be using the formulas anymore. So yeah, but basically we use the C0 as, you know, to produce entanglement on our quantum circuits. Okay, so let's move on to using Qiskit. I'm gonna show you how we do it in a second. So once you log into your account, I think I'm logged in. Yeah, okay. So you can see there are 9 points here at the top left. You click on those 9 points and you go to this menu and find the quantum lab. That's what we're gonna be using. So click on the quantum lab. It's gonna take a while because this thing runs on a server. So, and now you can start locating the things that you received on an email. So you should have received a zip file and a setup dot, which is a Jupyter notebook. Oh, this is taking more than I was expecting. Is everyone else already on the quantum lab? No? Yeah, okay. Okay, we can try it and go again. Okay. Everyone else online having problems? Or am I the only one? No?
For me, it's working.
For me too.
Okay, if that doesn't work. Is anyone here using Windows? Okay, and Ubuntu? Okay. Okay. Okay, I was not expecting this. Sorry.
Usually takes combine text ou ça?
I'm not sure. Usually it takes seconds, like
Okay.
5 seconds. So it's probably just a server error.
Can you use the API instead?
Yeah, I can try, but I'm not sure how to make it work on Windows. Tanya, are you there?
Yeah.
Do you know how to work with Jupyter notebooks on Windows?
Do you have VS Code?
So the ones that have Windows, do you have VS Code?
Or any other editor like PyCharm?
Google Colab. Yeah, I'm not sure if you can load Yeah, not everyone has a VS Code, so I'm not sure we can use that, but let's try Google Colab.
Just need to install Qiskit.
Yeah, that's the thing. So the ones with Windows, have you used Jupyter Notebooks before? No? Yeah? Okay. Nicola, do you know how to open a terminal in Windows? It should look like this. Ah, wait. Ah, ok. You know? Oui, c'est ça. Mhm. Okay. Okay, so the ones that don't have open the Quantum Lab or don't have installed Jupyter Notebooks and cannot use it from the terminal, try to open Colab. I'm gonna try something. Let's see if it works. On Colab, yeah. Yeah, just put like this. So you need to put a. I'm just gonna see if it works first. Hmm. Okay, so I'm not sure how to make it work on Colab. You know how to open a notebook? Because I tried opening one here, but it's not a notebook. I'm just like I'm just looking at the code, but that's not what I need.
Marco,
Yeah.
if you go on File and you actually open Notebook, and upload at the
Okay.
end, I think it's gonna work better. If you don't have it there, just upload it.
Okay. Yeah. Okay. Okay. Let's see if it works. Oh no, but Tanya, I think we're gonna have a problem because they're gonna need their access to the
Yeah.
to IBM, and I'm not sure you can do that from Colab.
Right.
Okay, this is working. Okay, this seems to be working. Let's see if this is gonna work. Yeah, that's the thing.
Yeah, I would need a save first.
What?
Like they would need to have access first to their account and get the token and save it for this to work.
Mm-hmm. Yeah. Okay, this is a bummer. Sorry.
Marco, even though you can't access the Quantum Lab, can you access the Quantum Composer? You know, the first.
Mm-hmm. Let me see.
Yeah, so the dashboard, on the dashboard, you know, if you go, you're not on the Composer, on the dashboard of the IBM quantum computing. So on the 9
Yeah.
dots, yeah, you should
Uh-huh.
have your access token there, and then just run one line on the Google Colab notebook, and it should be fine. I'm gonna
Okay.
put the line in the chat if
Dashboard.
I can.
Mhm. Yeah, okay, I see what you mean. Okay.
Yeah. I don't see the chat actually.
Yeah, I think we only have the Q&A. I think you can put it in the Q&A.
Okay, yeah. So just run this once and it may work.
Okay. Okay, let's try that. I'm gonna try it myself. If it works, I'm gonna tell you how to do it. And this should be a string. Okay,
Perfect.
it's working.
Yeah.
Okay, good. Okay, so can everyone open Colab? Yeah, okay, good. So what we're gonna do is here in File, we're gonna go to Upload Notebook. And there, you're gonna have to go and locate the files that you received. You need to unzip the zip file. You're gonna see a folder called CMAI _ QML. Inside that folder, you're gonna have this notebook that is called lab1 _ CMAI _ QML. You drag that to Colab and you put it there. Now that's gonna open this thing. And so the first thing we need to do is click on here, plus code. So that's gonna open a code line. Yes. Yes. How do you do that?
Could you please do it again? Slow.
Yes. Give me a second.
It's in the parameters.
There.
So language and ignorance, you can put the voice.
Okay. Okay, good. Okay, thank you. Okay, so I'll do it again. So you go to Google Colab. Colab. Okay, so if you do this, you Google Colab and get in there. You're gonna click on, what is it? Oh, yeah. Yes. So you need to click and file. I'm gonna wait 2 seconds for everyone online to follow. Then you click upload notebook. Then you're gonna drag here the lab1 from the zip file that you received. So you decompress the zip file, take the lab1 and drag it there. That's all you need to do. Is everyone okay so far? Good. Now here we're gonna push the plus code. This is gonna open a tab, and we need to put this sign and then pip install Qiskit. Then you click on this button that it's like a play button. It's gonna take a few seconds. This is going to install Qiskit, which is the library we're going to be using.
Marco, you have a question. If people can actually access the Quantum Lab, is it okay for them to use it?
Yeah, but they will not be able to follow me because so if they know how to use it, yes, go ahead. Because I will not be able to show them because I cannot open it. Okay. So once you finish installing Qiskit, then you go to the next cell, which is this one with all the inputs, and this should have a check sign on the left. Everything was okay. So you can see here that's a check sign on a green. So is anyone having problems with this?
Yes, I have no
Not yet.
access to the lab one. The first cell is like hidden.
What do you mean?
The code is hidden and I cannot see it and it doesn't seem to work. So, well,
So you tried this pip install Qiskit?
I don't see it. I will have to do it by myself.
Yes, you have to create it. So you have to click here on the plus code. This will open a tab for code like this one. And then you have to put the pip install Qiskit. So it says here it takes around 30 seconds.
That is working.
Okay.
Okay.
Okay, good. Okay, so I'm gonna wait for everyone to run this one with all the imports. So is it working for everyone here? Yes? Sorry? Okay, okay, good. Is everyone ready online? I'm gonna assume that's a yes. Okay, so if this is working, let's move on. Okay, so what we're gonna do is we're gonna inspect the iris dataset. So we're gonna be looking at how it looks in terms of the Python. So if we run the first one, what we do is this first line loads the whole dataset. The number of features that we have, this is the size of each one of the vectors. So we put it to 4. And here we're just printing a few examples. So with this slicing in Python, we're looking at the elements from 44 to 54 in the data set. So we see here that we have a couple of 4-dimensional vectors. And if we print the targets from this Python dictionary for the same, we can see the labels for each one of these samples. So the first 5 in here correspond to the class 0, and the last 5 correspond to class 1. So, and what we need to do is binary classification. Now this data set is very easy to manage because we know that only the first 100 corresponds to the 2 types of flowers. So we're gonna just slice this with this method from the lists. So we take only the first 100 samples. And this line, what it's doing is we're looking at, again, so the first 100 samples, but we're doing a normalization. So each one of these values, so if you remember here, we can have up to 5.1, apparently 7, and that corresponds to vectors that can have any length. But what this is doing is we're normalizing them. This is usual in machine learning. Now these vectors from X, these are normalized, so that means that they have norm equal to 1. Now, if I run this, you can see now, so I print the same elements, but now the values are different. And this is because we divided by the norm. Each one of these vectors, we divided by the norm. And now we have only 100 samples instead of 150 from before. And that's okay, because we'll only be doing binary classification. We only need 2 classes. Okay. Now here we're going to be using a function that is called train test split. This is from SciPy, or no, scikit-learn. And what it does is it's going to randomly shuffle the data set and it's going to partition it into train and test sets. So here, okay, so now you can see that for the train set, this is, so we have X train and X test. So these are the 4-dimensional vectors for the train and for the test. And the Y train and Y test, these are the labels. Now you can see that for the train, we have 80 samples. And for the test, we have 20 samples. Okay, so that means that we're going to use the 80 samples to do the optimization. And the other 20 is going to be to test our models, so to see how it well generalizes to unseen data. So if I go and look at the first one, okay, now it's already as a NumPy array, so this is no longer a list. And this is done by this function automatically. Okay, now here comes another part that you need to do. So here at the accessing the backend with IBM, what you need to do is so you need to, oh, sorry, go for the line that Tanya sent here. So I'm gonna copy paste it there. Now this token, I'm gonna erase it. And I'm gonna put 2, how these are called? So the quotations, yeah. And this is because the thing that you need to put in the middle is gonna be a string from Python. Now this token, you need to get it from your own account. Okay, so you go to the IBM Quantum, you click on the 9 dots, and you go to dashboard. Okay, now when you're in your dashboard, it's gonna say welcome and your name. And on the right-hand side, it says API token. And there's a button here to copy it. So you copy it, go to the Quantum Lab, and paste it there. Now it's gonna be a really big characters. And that's like your specific token to access your account. So you run this and it should work. Just wait a couple of seconds. Okay. Now here what I'm printing is all the backends that you have access to with this account. So you should see something similar there. Can you let me know if it is working for you? Yeah, okay. Yeah, so for everyone online, Tanya is putting the instructions on the chat. Thank you, Tanya. Okay, is everyone able to load their accounts? Yes. Okay.
No.
Good. No?
No. I'm doing the token, I copy the token, I paste the token, I'm doing same things, but give me an error.
Did you put the quotation
load
marks?
account takes 1 position argument, but 2 were given, so.
Did you
This
put
is
the
clear.
quotation marks for the token? Yeah.
I'm used to work with Python, so yes, I did it, but this is a kind of error that used to be a lack of some information. The function,
And,
so I don't know.
Yeah, I'm not sure what's happening to your account. So you have exactly what I have here.
Yeah.
And it's not working. So if that's the case, I suggest you open the lab again, like close everything and open it again and follow the instructions again. Because if you have exactly what I have here, it should be working because it's working for me.
Okay. 2 minutes. I'll be back. Just go on and I go back to you.
Yes.
Thanks.
If you keep having problems with this, put it in the Q&A. Tanya, can you take care of it, please?
Yes, I will.
Okay, thank you. Yeah, maybe you can put a screenshot of if it's not working.
Yes.
Thank you. Okay. So I'm gonna wait a couple of seconds for everyone to be on the same page.
It's working.
Okay, good.
I reload the whole page and it's working. I don't know.
Okay, good. So
Thanks
I
for
guess it's working for everybody else. So just to let you know, so this IBM Q, this is the library we're using from IBM. It helps you like log into your account and give you access to the backends that we're going to be using. In this case, when you get this provider from this IBM Q.get provider, you put a couple of things there, and these things are linked to the type of account that you have. So that's why you see just a few of these values. If you have another type of access to IBM Q, and then you will see other type of devices here that you can access to. And with this .backends method, that gives you the backends that you have access to with this account. Now, what we're gonna use is the first one. This one is called the IBM Q Casson simulator. And this simulator, what it does is simulating all the vectors from the qubits and the matrices. So if you run this one, you should have a check sign there. And now what that is doing is loading this Casson simulator to this variable Casson sim that we're calling. Okay, so now, so now what we're gonna do is we're gonna start drawing the quantum states on the block sphere. So for the first part, I'm gonna start a quantum circuit. So this is how you load, how you create a quantum circuit with this class quantum circuit, and inside I put a 1. This is the number of qubits. Now, what this will do is create a quantum circuit for just 1 qubit. And when you use this dot draw MPL method, this is going to draw the quantum circuit. Now, this is not working.
Yeah, say you need to, when you install Qiskit, you need to use the option for visualization. So
yeah, you're right. Okay.
you have to put more heads with
Okay, so what I'm gonna do is, so below this get provider, I'm gonna add another plus code there, and pip install Qiskit brackets visualization. Okay, Tanya, can you put this on the chat, please? I'm gonna. Thank you. So you should be able to run this. It's gonna take a couple of more seconds. Okay. And I need to install.
when you need to start. It's working for me, but you need to restart It's no big deal if you do runtime restart.
Okay. Let me see.
If you install new libraries, you need to set the
Okay. So runtime.
start runtime.
Okay. There. Okay.
But you need to
Run everything again.
yes.
Okay.
It's annoying, but
Yeah, I know. Sorry.
it's working on the side.
Okay. So I'm gonna rerun this. Okay. Yeah, so, okay, so sorry about this again. So once you installed this pip install Qiskit visualization, what you need to do is go here to the runtime menu and click on restart runtime. And what you need to do is go and run every cell again. Now, when you do that and come back here and run this, now you should be able to see an empty quantum circuit. So I'm gonna wait a couple of seconds for everyone online to follow. Is it working? No? Is it working for everyone online? Is it working? Okay. Ah, d'accord.
No.
Not working?
No.
Can I see maybe the error or something?
Okay. So is it working for everyone here? Yeah, okay. Yeah, okay. Okay, good. Okay, I think so. Should we continue? Is everyone online following? I'll assume that's a yes. Okay, so now that you have this empty quantum circuit that prepares the zero state, and with the next line of code, the next cell, when you run it, you're gonna see a block sphere. So basically what you have to do is you have to create a Python function that returns the quantum circuit. And this state vector is a class from Qiskit that is gonna receive a function that gives it a quantum circuit, and it's gonna give you a state. So the state is basically the vector that represents the state that is prepared by your quantum circuit. Now, when you use this method, plot block multivector, and give it the state, this will plot the state on the block sphere. Now, as you can see, this quantum circuit starts with the qubit on the state 0. And that's what you see on the block sphere. So you have the representation of your qubit on the block sphere pointing to the north. Now, the X gate. So in this case, the function that we're going to use, we're going to create a quantum circuit and apply an X gate. But here you have an index. This index means the qubit to which you're applying this. And the indices will start on index 0 instead of 1. So even though for the quantum circuit it passes a 1, that means we're using 1 qubit. But when we do this qc.x, this means apply an X gate on qubit 0. Now, when you run this, you will see that so you start with your qubit on state 1, you apply the X gate, it moves to state it moves to state 1. And this is what you see on the block sphere. Okay. So actually, let me go up. Now the quantum lab is working. So I'm going to go to the quantum composer and do the same thing, but here. So you start with the qubit on state 0, you apply the NOT gate and moves to state 1. Now, these things that you see here on the histograms is what you're looking at on the block sphere now. So applying an X gate to the qubit 0, you do it like this in the code. And this is exactly the same thing you were doing here on the quantum composer.
So when you say quantum circuit 1, it means 1 qubit.
This is, yes. So this is number of qubits. Yes. So if we go to the next one, okay, so here for the next cell, this is going to plot the quantum circuit. So as you can see, this is the circuit that we have. So in this case, the X gate is no longer this plus with a circle. It's just an X on a square, but it's the same gate, just the notation is different. Okay, so now let's move on to, now we're going to use the Hadamard gate. So, and the way we do it is we create a quantum circuit with just 1 qubit. So again, this thing means number of qubits. We're using only 1 qubit. And by doing qc.h, this means apply the Hadamard gate. And as a variable there, we pass the 0. So that means we apply the Hadamard gate on qubit 0. Now, when we run this, this is going to show the block sphere with this superposition. So as you can see, is the vector pointing in the direction of the x-axis. And when you do this block H, the function that we define that creates, that gives us a quantum circuit that produces superposition, this is going to produce the visualization of the quantum circuit. So the quantum circuit that does this is just 1 qubit with 1 Hadamard gate. Okay, now we can do the same thing. We can produce the other superposition, the one that points the other way around on the same axis. Here what we do is we first apply the X gate to qubit 0 and then the Hadamard gate. So as you remember, this is going to produce a minus sign on the one state. When you plot this, then you're gonna see a vector on the block sphere that is pointing on the other side of the x-axis. And if I draw the circuit, then you're gonna see you have a qubit, you apply the x gate and then the h gate. Okay, so far so good. Now with this one, we can prepare exactly the same state because so when we apply the Hadamard gate, so this we apply the Hadamard gate to qubit 0. This produces an equal superposition, and the C gate will change the sign of the one state. So this will produce the exact same state on the block sphere. So this is the same as we had before, but the quantum circuit is different. Okay. So actually, let me draw this. So if I create another cell there and I do dot draw MPL, then the quantum circuit is now H gate and then the C gate. Good. Now, let's move on to other type of rotation. So let's look at the rotation around the y-axis. So again, we create a function that creates a quantum circuit with just one qubit. Now, this .ry method, it receives first the angle that you need to turn this qubit in that specific axis, and then the qubit. Okay, so that's why you have here pi over 5. This is the angle that we're going to rotate, and on the qubit 0. Now, when I run this, you can see, so this is supposed to start on the 0 state, and you rotate along the y-axis by pi over 5. So you can see this one is rotated along the y-axis. Now, if I draw the circuit, it's going to look like this. So it's an RY, and I'm going to zoom in, and you can see here I have pi over 5. Can you see it? So this is how you put other type of rotation. So for the RX is very similar. Actually, you just need to change the Y for an X. And again, you pass first the angle of the rotation and then the qubit. So you run this, and now you can see, so I rotated along the x-axis, a qubit that was pointing to the North Pole. And this was with an angle of pi. So that means you rotate it all the way to the south. And this is the same thing as just applying an X gate. Okay. Now here, if I zoom in, you can see I rotated by pi. Okay. What else can we do? Okay, now let's do an example with more than one qubit. So in this case, what we're doing is this quantum circuit is going to receive 3 qubits. Now the qubits are labeled starting from 0. So first we're going to apply a Hadamard gate on qubit 0. This is this line. Then the next one, this is a control NOT gate. So the control NOT gate is, you call it by doing dot CX. And the first qubit that you pass there is the control qubit. And the next one is the target qubit. Now you apply one CNOT control on the 0 qubit and then apply it on the 1 qubit. And then you apply another CNOT control with the 1 qubit and target the second qubit. Now we would like to, wait. So I'm gonna comment this line, and when you draw this, okay. So this is the circuit that you're preparing. So first you apply the Hadamard gate on qubit 0. This is the first line. Then CNOT controlled on the 0 qubit. So this is this part of the code. And the target of that CNOT is the qubit 1. So that's why you see this first CNOT there. For the next one, you have control on the 1 and target on the 2 qubit. So this is the second CNOT. Now, when I put this method measure all, this is going to measure all of the qubits. So if I do this now, You can see now this puts a barrier, like just to separate. The barrier does nothing, only is a visualization tool. It separates the part of the qubit that you build and then the measurements. So in this case, you're measuring these 3 qubits. Now, so what this circuit is doing is preparing the state that you see here at the bottom. So as you can see, the only things that you can measure is the all zeros state and all ones state.
Is there a way to visualize
For more than 1 qubit, no.
No, okay.
Yeah.
For 1 qubit.
Yeah, the block sphere is just for 1 qubit. And the problem with the visualization is the tensor product.
Yeah.
Because you do the tensor product, now you have a 4-dimensional thing, and it's not easy to visualize.
get the state vector.
You can visualize the state vector with the simulator. Yeah, but that has a limit. In the real quantum computer, we do not have access to the state vector.
Okay.
Yeah.
Just a quick question.
Yes.
In the image, what means the 0, 1, and 2 at the end of the arrow down the measurement? Does it mean do it mean something or?
Yeah. So what it means is that in this miss is an abbreviation for measurement.
Okay.
So you have a slash there, a small slash, and a 3.
Mm-hmm.
So that means you're having like 3 transistors in which you're going to save 3 values measured from these 3 qubits. The 0, 1, and 2 means you're measuring on different transistors. So you're saving the value, which is either 0 or 1 for each one of the qubits, and you're saving them on different places. That's what it means.
Okay, thanks.
Yeah. Okay, now what we're gonna do is we're gonna run this circuit on a simulator. Okay, now this execute function receives first the quantum circuit that you want to run. The backend is going to be the QASM simulator that we already loaded from this provider IBM Q with your account. The shots is, remember, when you have a quantum system, you can only predict probability, so you have to run your experiment several times. In this case, we only need to run it once for this example. And we pass a seed because, so we're using a simulator. Now the simulator is doing some probabilities, and we all are using the same seed. So this means that we're gonna be producing all the same probabilities at the end. So this is so that we all have the same results. Okay, this is only because we're using the simulator. So if I run this, so you can all try it. This is going to run the circuit, and this is going to send the circuit to the QASM simulator, which is on the cloud. It's going to wait for the result. And when the result comes back, you're going to have a check mark there. Now, this result object has a method that is called .getCounts. This is going to give you the number of counts that you have for zeros and ones for each one of the qubits on the number of shots that you did. So the number of shots is the number of times that you run the experiment. In this case, we only run it once. So when you print this, you can see I got, for the 111 state, I got 1 count. So this is what this dictionary means. So you have as keys, you have the possibles measurements from zeros and ones. And as values, you have the number of counts that you have that state on your experiment. We also have this plot histogram method that allows us to plot the number of counts. In this case, it's very simple because we only measured one of these states, which is the 111 state. But this is not allowing us to see the superposition, because this state that we prepared, this is a superposition between 000 and 111. So we should have both. If we run it several times, we should have both results with how much probability. We have the coefficients there, right? So we should have the 000 state with 50% probabilities, because we need to square this. When you squared 1 over square root of 2, that gives you 1/2. The same thing for the other. So we should have the 000 state and the 111 state, the same number of times approximately if we run it more than just one. So for the next cell here, we're running the same experiments 1,024 times. So if I send this and wait for the results, this is going to get the counts, print the counts and the histograms. So now you can see that for the 0,0 state, we have 511. For the 1,1,1 state, we have 513. So it's roughly 50-50. Okay, so this is your first exercise. Okay, I need to open this. Okay, so your exercise is you have to build this circuit. Okay. And then run it on the simulator.
Sorry, I'm getting result none from the
Yes.
I'm getting result none from the execution.
On the cell for the
first
exercise?
Example. Yeah, the exercise. No, in the example, what we do just one shot.
This one?
Yeah.
Where do you get a none? There?
Yeah, result is none.
Did you got the results? So this line run and you had the check mark there on the left?
Yeah.
And you have
then
exactly what I
result.
have here.
Yeah, then I print result in between because I was getting error because count is empty. Then I print results. Result and it is none.
Okay, so that means you still don't have your results from the backend. So
that's used to happen, or just I'm having bad luck today.
I think you're having bad luck.
Good.
Yeah, sorry, that doesn't really happen that much on the quantum lab. I'm not used to this Google Colab. So I just restart the kernel on the runtime. Click on restart runtime and run everything again. Sorry.
Yeah, that's fine.
Oh, the exercise there. Okay.
Over 600.
Yes. Pi over 6.
So the plus on the line 2 on the qubit 2
is the NOT gate. The
so
X.
The X.
Yeah. Okay. Anybody else finish?
It's working.
Okay, good.
A question, but so
Yes.
you have a circuit here, there is a formal solution that you can write the equations and get
Mm-hmm.
the equivalent of what you showed before for the state vector. Is there a function in the API where you can do the symbolic calculation and get
The vector?
yeah
The equations, no. Only the numbers at the end.
numbers?
Yeah.
Okay.
The vector with the numbers. Yeah. Yeah. No, but so actually for quantum machine learning today, we don't have like that kind of control over the vectors. So it doesn't really make sense to write everything like formally if you want to do QML.
Yeah.
Mhm.
That's
Yeah, for today, we're going to look at some examples in which this is going to help. But in general, when you want to go for bigger circuits,
Yeah.
this is not going to be helpful. Okay, so everyone finished with the exercise? No? Do you need any help? I can. No? Sure. Okay. Okay, so what I'm gonna do is solve it myself. What do you think? Okay, so here I'm gonna put quantum circuit with 3 qubits. Then is QC dot Hadamard on the 0 qubit, I guess. Yeah, okay. I need to find a way to look at this. Okay. So that's that. Then QC dot Rx of pi over 6 on qubit 2. Then I think I'm gonna follow the order by qubits. So QC dot Ry on pi over 3 on qubit 0. And then QC dot C on qubit 0. So that's for qubit 0. Now for qubit 1, we need a C naught, but after we apply this to the second qubit. So first the Rx, then QC dot H on the qubit 2. Then we apply QC C naught, which is Cx, but the control qubit is qubit 2. So this is 2. And the target qubit is qubit 1. So I put a 1 there. After that, I do QC.X, which is the last X gate on qubit 2. And then QC.measure all. Now, if I run this, I would see this one. Now, the only thing that changes is the colors and the notation for the NOT gate. Okay, so instead of being this plus, now it's the X with a square. So that's that. And if I run the circuit there, I forgot how to do it. I think it's like this. So here my quantum circuit is QC. I run it for 1,000 times. And wait for the results. And if you're using the same seed, you should see this. Okay, now this is the results that we put there. Now we know you have those results because we're using the seed. If you were not using the seeds, you will get like approximately the same probabilities. Okay, so everyone good so far? Are you sure? Yes.
Gate in your example, but in this case, you didn't create two gates.
Do you mean?
No.
Ah, so you mean this one?
The next.
The one on the top? For which qubit? Qubit 2. And this plus? Yeah, so this plus is the same thing as this X gate. Yeah, this plus gate, X gate, and NOT gate are the same thing. Sorry for the confusion. Okay, so everyone good so far? Yes? Okay, good. Now, let's go back to the presentation. So what we did was we inspected the iris dataset. We took only the classes that we're going to be using. Then we started looking at how to visualize this on the block sphere, how to visualize states on the block sphere. This works for only one qubit. And we started building quantum circuits using Qiskit and run this on a backend on a simulator in the cloud. And you already built your first quantum circuit and send the results. So now what we need to do is we need to be able to put the data in a quantum state. And we call that the quantum feature space or the data embedding. And basically, we have the data on a Euclidean space. I'm going to close here. And what we want is we want to have the data in the block sphere. And we have two ways of doing this so far. We have angle embedding and amplitude embedding. Now, the angles means for the rotations for these gates, the RC, RX, RY gates, the angle, you can put there the data, for example, that's called angle embedding. And the amplitude embedding is when you write down the direct notation, you have some coefficients that gives you the probabilities when you square it. And those are called amplitudes. So we could put the data as amplitudes there.
Can you mix the two?
Yes and no. But let me explain each one of them first. So if you start, so this is called the angle embedding. So if you start with a classical input vector, so you have a 4-dimensional vector, we're going to be using 4 qubits. And let's say we have a rotation for each one of the qubits. And basically what we do is plug the values as they were rotations. So we do this, and this prepares a quantum state that we call phi of x. And this is a quantum state that depends on your data. Now, the disadvantage is you need as many qubits as you have features. So if you have an image that is 28 by 28, that will give you 784. You will need 784 qubits to put an image which is 28 by 28 if you do this. Okay? So n features can be embedded in the rotation angles of n qubits. Actually, this should be the same n. So you need n qubits for n-dimensional vectors. For amplitude embedding, this seems like a better idea. So what you do is you write down your vector as a linear combination of the basis states. Now, if you remember, each one of these vectors corresponds to the 0, 0 state, 0, 1, 1, 0, and 1, 1 state. And the coefficients are going to be these xi's from your data vector. But, so yeah, so in terms of a quantum state, you will look at it like this. And basically, so we already normalized the data. So the norm is equal to 1. So that means we can just go and plug in these values as if they were these alpha, beta, gamma, and delta. So that will give us a state that corresponds to this data vector. Now, as you can see, I used only 2 qubits for this case, and I'm using 4-dimensional vectors. And that's because this scales as the log of n, where n is the number of qubits. Okay, in this case, we had 4-dimensional vectors, log of that is 2. So that means we need 2 qubits to embed the data like this. But there is a huge catch on this, okay? Now, let me explain why. Let's say we start with this, you have this data feature, okay? Now, this is not realistic if you look at the iris data set, because the first one is the measure of the petal, the other one is the width, the other one is the sepal length and width. So that means you have zeros there. So this is not realistic. This is just an example. Okay, now we need to normalize this. This is already normalized. And the quantum state that represents this vector as an amplitude embedding is just the 0, 0 state. And what's the quantum circuit that prepares this? Is very simple. You just do nothing on 2 qubits. Good. Now let's say you have a vector like this one. Again, this is non-realistic for the iris dataset. But let's say you have a vector like this. You have to normalize it. Then you end up with a vector that looks like this. In terms of the Dirac notation, this is an entangled state between the 0, 0 and the 1, 1 states. How do you prepare this? We already know. Hadamard gate and then a CNOT. What about this one? So we need to normalize it. You divide by the norm. Apparently, it's 1 over the square root of number. And the quantum state in terms of the Dirac notation will look like this. How do you prepare it? That's the catch. Okay. So you have to apply something to prepare the state, and we have no idea how to do it. Okay.
So that's a combination of
Yeah.
quotations.
Yes. Yeah. There are algorithms to do it, but they're not efficient. And
probably it's not a unique transformation. Yes.
What?
Is it possible that the U matrix you showed, you have several solutions for the U matrix?
Yes. Yeah. There are several solutions, but it's highly non-trivial to do it. Okay. Yeah. Also, if you try to run it on a real quantum computer, then if you have too many, then your state will decohere. And you have noise, so you really don't have control over it. Okay, let's go to the second lab. We're gonna do the same thing. So I'm gonna do file on Google Colab, then upload notebook, and I'm gonna drag the lab 2 from the zip file that you decompressed. I drag it there. It's gonna open. Good. Now, if I run the first one, will it be working? Damn it. Okay.
The same
thing.
visualization.
Yeah. Pip install Qiskit, and then pip install Qiskit visualization. Okay, sorry about that. So you first need to run this 2 lines on the new notebook and wait for around 30 seconds. Okay. So if I go there, try to run it. Qiskit machine learning. Yeah. Okay. So there's another thing that we need to install. Pip install Qiskit machine learning. I hope everyone's following this. So you need to install again Qiskit visualization, and this other one, which is Qiskit machine learning. Okay, this was fast. Tanya, please put this on the chat so that I can follow here.
Yep.
Thank you. Okay, and now we need to restart the runtime. Okay, so after you do that, we go to the runtime menu and click on restart runtime. Click on yes. And cross our fingers.
You see, you need to upload the GUIN file.
Yes, okay. Yeah, you're right. Okay. So this is not working because we're lacking one file. So
In fact, you go
in this, yeah, so you click here on the folder on the left. And from the zip file that you decompress, look for the utils.py and you drag it there. So, okay. Okay, now if I run this, yes, so now it's working. So again, you click this folder on the left, you drag the utils.py from the file that you got, the folder that you have, and now you should be able to run this. Is everyone able to do this? Yeah, is it working? And online, is it working? Is that a yes? Okay.
Yes, it's working.
Okay, cool. Thank you. Good. So now we're gonna create a dummy dataset. So this is going to be just a dataset that is going to be one-dimensional. So if I put play here, this just creates the two types of points, the x0s and x1s. Number of features, in this case, these are like one-dimensional vectors. So these are just correspond to just one number each. And I'm gonna plot it here. Okay, so this is the data set that we created. Now, we should be able to, for example, we would like to classify this with a linear classifier. So this means we should be able to draw a line separating the two data sets. Now, in this case, it's not possible. And but we can do it if we put this on the block sphere. So I'm gonna show you how. So the first thing is we need to create a vector of parameters from this parameter class in Qiskit. Now, what this is doing, you call this parameter class, and that puts this formatted string with the name. So this has x and then a string of I. So this is just the name of each one of the parameters. Now, the next part is creating a quantum circuit that depends on the number of elements of each one of the vectors. That's the number of features. In this case, it's just one. So this creates a quantum circuit with just one qubit. Now here, we are applying an Rx gate that has one of these parameters on each one of the qubits. So when I run this, you can see I have one qubit with one Rx gate and this x0. Now x0 is the number of the parameter. So a parameter is a value that that gets, when you use this class parameter, it allows us to change the value of this parameter. Okay, now this we're gonna be using this simulator. Now, this is not the simulator on the cloud. This is a simulator that is going to run on this notebook.
You need to connect.
No, because this is a local simulator. Yeah. So yeah, so in this case, you get this custom simulator and the state vector simulator. So the custom simulator will give you the probabilities at the end, and the state vector simulator computes the whole vector and the whole matrices for each one of the gates and the qubits. Okay, now from this function get state vector, you're gonna give it a couple of things. So first you pass the quantum circuit. Now the data that you want to put on a quantum state, the parameter, which is this vector of parameters that we have at the top here, and the simulator, but this is going to be the state vector simulator because we want to visualize it. So we run this, and now you can see that my data lives in the block sphere. Okay, so this is what these state vectors 0 and state vector 1 are doing. So state vector 0 is everything that was from the class 0, I think is the blue, is loaded with this state vector 0. And for the red one, this state vector 1. Now you're visualizing all of these points in the block sphere. Now here you can see that if I draw a line or a plane, I can separate the red from the blue. Okay? And this was not possible before. So this is one of the ideas of machine learning in general. You have your low dimensional data and you put it in a high dimensional space. And you hope that in that high dimensional space, everything is separable and the classification is easier. In this case, the space that we're going to be using is either the block sphere or what we call the Hilbert space, which is the space in which qubits live. So what about the iris dataset? So I'm going to load the iris dataset here. I'm just showing one of these vectors. And we're going to use first the angle embedding. So this function, what it's doing is, so you receive a quantum circuit and a feature vector. So that means one data sample, so one 4-dimensional vector. First, we check that the number of qubits that we're using is the same as the dimension of the vector. Because for this, we need, for 4-dimensional vectors, we need 4 qubits. So that's what this line of code is doing. So number of features must match the number of qubits. So if that's the case, then we apply an Rx gate where each rotation is given by each element of this vector on different qubits. So if we run this, should be working. Now, in the next cell, what we're doing is we're taking the first one from the training set. So I'm looking at the 0 vector from the training set. This corresponds to only one 4-dimensional vector. If I run this, you can see that now I have this data embedding that goes to the angle. So here I'm printing these vectors, so features for the first data point. These are the features. These are the values on each one of the coordinates. And those are the values of the rotations of the angles here. So this is how you build the quantum state using what we call the angle embedding.
Angles have to be.
It doesn't have to, but these gates are, since these are rotations, you have a period of 2 pi. So if you go too high or too low, it's the same thing as if you just normalize them. You see what I mean? Yeah, okay. Yeah, but usually what we do is we normalize the vectors before doing the embedding. And this is, again, this is done general in machine learning. It doesn't have to be quantum machine learning. Okay, now let's move on for the amplitude embedding. So again, if we have, for example, this vector, how do we prepare it? So we know that this is a superposition. This is one of the examples that we saw. We prepare it with the circle like this, a Hadamard gate, and then a CNOT. So that's that. Okay, now we're gonna try to use this amplitude embedding. Now, as I said, there are methods to do it. One of those is this raw feature vector. So if I run this, you can see we have a big gate there that says parameterize, initialize, and it receives 4 feature vectors. So you have 1, 2, 3, 4. But this is a black box. So it's not telling us which gates we need to apply. So when we send it to, for example, if you send this to a simulator, this will be really easy because you just need to plug in the values on the vector. But on a real quantum computer, you will need to apply several different gates to prepare the state that has these amplitudes on each one of the base states. And this is costly. Okay, so unless you're using a simulator, this thing will not be optimal. So, okay, so if I apply here, yeah, now this is just with this corresponds to just parameters, and here I'm just plugging in one feature vector. Now here again, you cannot see the values. You can see that apparently this thing will prepare a state that has these values as amplitudes, but it's not telling you how to do it. Because it's doing it like, I don't know how to call it, like virtually on the simulator. So since it's a simulator, you have vectors and matrices, you just plug in the values. And that's why it's easy to do on a simulator. Okay, now there are other methods to embed data, and most of them use angle embedding because amplitude is embedding is hard to do on a real device. So we have several examples. So we have the C feature map. So if I plot this one, so this has several things. So feature dimension, again, the number of features is the number of elements in your vectors. So yeah, so what we call a feature is one element of the, yes, for example, for the flowers, one feature is the width of the petal and the length of the petal, that's another feature. So that means for each flower, we're representing it with 4 features. So these 4 measurements. So we pass it here, the number of features, and then this reps equal to, it's how much, how many times you repeat the circuit that does this embedding. Now, this is done in a couple of papers. But again, you have to be careful if you're running a real quantum computer. You don't want your circuits to be too long. So if let's say I change this for 1, you can see I only have these 2. So you start with your qubits, all your qubits in superposition, and then you apply this P gate, which is, it applies a phase. So that means you multiply your vector by a value that it has norm equal to 1. So it doesn't changes the probabilities. But when you do all these computations all together, that it will change the probabilities at the end. Just as when we did quantum teleportation, you see when there are times where the -1s, even though when you square it gives you the same thing as 1, for the final computation is important, is the same thing here. So if you use only the P gate, it will not do anything in terms of probabilities. But if you combine it with others, it will do something different. So again, here I can put 5, for example, and it will create a deeper circuit. We also have this called a poly feature map. Again, you pass it the feature dimension. So this is the number of features. In this case is 4 for the iris dataset. And then you pass it the type of entanglement that you want to use. And in this case is linear. I'm going to show you what it means. Okay, so linear entanglement means qubit 0 with qubit 1, then qubit 1 with qubit 2, then qubit 2 with qubit 3. So it's just a way to call this type of entanglement. And basically what it does is start with all your qubits in superposition, then apply the phase gate, and there's this entanglement between the qubits. Now, here, look at the values for this P gate. So it's 2 times pi minus x0 times pi minus x1. So in this case, you're like combining features, different features on your vector on the same rotation. And the same thing for the other. So here you're combining 1 and 2, and the last one is, I think, 0 and 3. So that was this poly feature map does. And again, this is still angle embedding because we're putting the data, even though we're combining the data in a different way, it's still on an angle rotation on our qubits. Hello. Sorry about that. Is there a question? I see someone raising his hand. Okay, good. Okay, so this, okay, so after this poly feature map, what we're gonna do is just place instead of these x's. So these x are just parameters. So we're gonna put there the values from the actual data, and we do this with this method, the assign parameters. So basically, what it's doing is looking at the parameters in the circuit and plugs in the values, the specific values for your data. So when I do this, now you can see that instead of having these expressions, now you have numbers. Okay. Good. Now here's your exercise. And you have to embed this vector, which is given here, using the CC feature map that I introduced before. So I'll give you a couple of minutes. Is there a question online? I think someone is unmuted. I'm not sure if you were gonna ask something or forgot about your mic. Is it working? Okay, so everyone good so far? No? So I have the solution now here. So basically what you have to do is write down this data point there. So I wrote it down like there, like that. And you have to normalize it. That means divide by the norm. You can compute the norm using numpy dot linear algebra dot norm. And then you pass it to this CC feature map. Oh yeah, actually I'm lacking one line. So you have to give it the number of features there. And then you have to do this assign parameters method there. Okay. Just copy paste this one. So I'm gonna do cc circuit dot assign parameters and pass the x vector. Now, when I plot it there, it has only parameters. So that's what you can see, x0, x1, x2. If I run this, this should have the values or not. Oh, okay. Yeah, I think I need to put it in place. So true. There it is. Actually, I didn't tell you how this works, so I'm gonna put this one like this. Yeah. Yeah, so this method returns a quantum circuit. So I've saved it in the same variable. Now I plot it. And now you have numbers there. Is that clear? Not really.
It's like if we have another flower kind of data, right?
Yeah. Mhm. It's not the circuit you're getting?
Just one level, because
Are you using CC or C feature map? Okay. If you copy paste the one from above, that was a C feature map. Here I'm using CC.
Okay.
Yeah.
Okay.
Oh, it's a longer circuit. Mhm. Yeah. Okay. So I guess we can have a small break. Let's say 10 minutes. Okay, good. Then we're gonna move on to doing classification. Okay, Muy bien.
Envie de préparer la température des 2 prochains jours.
Si c'est sur le jour.
Okay, I think we can continue. So we'll probably not do all of the. We'll probably not finish with the whole presentation today, but we can follow up on the next Thursday. Okay, so we've been looking at how to embed the data on a quantum circuit. Now what we want to do is we want to create a classifier, because so far what we did was taking the data into a quantum state. And the classifier should take data and gives us a label. So there's still a missing part here, which is how to go from the quantum state to a label. Okay, now remembering what we do with the qubit. So when we measure a qubit, we can obtain either 0 or 1. And if we obtain 0, let's say, we can say, okay, this corresponds to class 0. And if we obtain 1, then we can say that corresponds to class 1. But the thing is that the measurements are probabilistic. We don't know when we're going to get 0 or 1. And we'll probably not be using only 1 qubit. So if we go to look for more qubits, let's say we use 2 qubits, we can obtain 4 different measurement outcomes. And so these are all the outcomes that we can have. And we need a way to decide what's the label based on these measurements. One way to do it is only looking at the first qubit. So you measure only the first qubit, and that measurement tells you what's the label. Of course, all of this will be like in terms of the higher probability for each one of those. Or we can look at the parity. Like if we have just at the parity of number of ones that we have. So for the first one, this 0, 0, we don't have ones. So that means we have class 0. For the last one, we have 1, 1. So that means it's the same parity as having 0, 0. So that corresponds to class 0. And the others correspond to class 1. Yeah, so the outcome of the measurement of a quantum state, again, is probabilistic. And we have to repeat the state preparation and the measurement many times. So we build a quantum circuit, we put the data, we run the experiment, that several times, and look at the probability distribution at the end. And the result will be a probability on this specific sample of data of being of either class 0 or 1. And we need to do that for each one of the samples on the data set. Now, how will this will work is we prepare the quantum state with just one of these samples from X, and we repeat the experiment n times. We measure it, we save it in a variable m. If it's 0, we increase the number of zeros that we have. If it's 1, we increase the number of ones that we have. And at the end, we compute probabilities. So we average over all of this. And that gives us P0 is the probability of the input X being from class 0. And P1 of X is the probability of the input X from being on class 1. And how do we decide the output? Well, we can look at the probability, for example, from the 0. If this is greater than 0.5, then we say it's from class 0. And if not, if it's less than this, then we say it's from class 1. So we only need to look at the first one. In this case, because if we only use one qubit, we only have two possible outcomes. So we only need to look at the first probability, for example. Yeah, so this will be like the whole the first picture of a quantum classifier. So again, the story is you take an X, you build a quantum circuit with it, so you end up with a quantum state. You prepare this state several times, count how many times you have zeros and ones, compute the probabilities, and now based on the probabilities, you make the decision. Now, there are several things that can go wrong. Now, I'm going to show you one example. Let's say your data set has only 2 points. And these are the points that once they're normalized. And you use this feature map to embed your data. So this is a Y rotation, and you embed your X as X times pi over 2. So for the first point, you end up with this superposition. So this is the same thing as apply a Hadamard gate. And the other one is the other superposition. So you just flip a sign on the one state. Now, as you can see, these values on the Bloch sphere lie on the equator, on the x-axis, both of them. So what will happen when you measure? Now, for that, I need to tell you what the measurement is really doing. When we measure along the z-axis. Now, what that means is that the probabilities of these points, when we measure it several times, is going to depend on the height on this z-axis. So yeah, so this is looking at the z-axis. And yeah, so this is measuring the height in the Bloch sphere. Now, what that means is, okay, let's say we measure on the z-axis and your qubit is at the top. So that means the probability of measuring the state 0 is completely 100%. If it's at the bottom, you have 100% of measuring the state 1. And if you have something in the middle on the equator, then you will have 50-50. And if it's a little bit above that, then your probability of measuring 0 is a little bit bigger than your probability of measuring state 1. And that's because we're measuring along the z-axis. But we can also measure along the x and the y-axis. So in this case, so I showed you how to measure along the z-axis. The same thing will happen for the x-axis. So you will measure now along the x-axis. And you can also measure along the y-axis. But there's another catch. The quantum computers today only allow us to measure on the Z basis. So that means that if we have a data set that looks like this, we will not be able to differentiate between the two. Because what we're doing is measuring the probabilities of each one of these, and they both have 50-50 probabilities from class 0 and class 1. So we cannot decide between these two. But if we somehow can measure along the x-axis, this will be solved. Because now along the x-axis, these two classes are separable. Or we can rotate the qubit instead of measuring along the x-axis. Because all of these gates, remember, these are rotations along the axis. So once we have the data set in the qubit, and we know that we can measure only along the z-axis, we can apply a rotation so that now the values that we want lie on the different poles that we are measuring. So in this case, if we rotate the qubit, now this the red one will be to the North Pole and the blue one will go to the South Pole. Now, when we measure here along the z-axis, now we can differentiate between the classes. And we do that by applying another quantum gate. So this W, in this case, this will be just a pi over 2 rotation that will allow us to rotate the qubits, the state of the qubit as we want. But in general, we don't know which one we need because this will depend on the data set. So if you change the data set, this was just one of the a small example. And if your data set is more complicated, you don't know in which basis you need to measure, like what kind of rotation you need to do to your qubit before doing the measurements. So what we do is, so first you put the data embedding circuit, and then you apply this change of basis. Change of basis is another way of saying rotation of the qubits. and then you measure. And the measurement is always along the z-axis. We call this a measurement in the computational basis because of technical things, but that is not important for now. But the thing is that this W, we don't know what it is, but what we can do is parameterize this rotation. So let's go for the next lab, and we do the same thing. So file, upload notebook, you drag the lab number 3. Once it's there, you need to do pip install Qiskit, then pip install Qiskit visualization, and pip install Qiskit machine learning. Click on play. Okay, now once this is done, it took 45 seconds for me. Now you have to restart runtime. So you click on runtime, restart runtime. Yes, and now we can start. So if we go to the first cell, just check that it works for all of you. It's not working for me. Oh yeah, I need to, yeah. So you need to upload also the utils here. So you click again in the folder, you drag the utils.py there, and try running the code again. Okay, now it's working. Is it working for everyone else? Yeah, okay, good. Then this thing again, this gives us the simulators. These are local simulators. So we will not be doing this on the cloud. And okay, so now this will produce a data set that, okay, so now this data set is the one that we want to classify. And we'll be using angle embedding. So I'm going to move to the next cell. And this what it's doing, this is applying. So again, the number of features is the number of qubits we're going to be using. This is applying a minus x rotation, or sorry, y rotation on minus each one of the elements of the vector. Again, so this minus one, this minus, it's just something arbitrary that put there. We can put like in the example that I showed you, it was x times pi over 2. So you can put some factors there to play around with the data. We don't know which one is the most optimal, so we need to try several. In this case, we just try this one. And then I draw the picture. So here what I'm doing is, again, I'm declaring a vector of parameters. And I'm passing this function. So I'm passing it this function that I defined before. I'm passing it the parameters and the number of features that I have. And it produces a vector, quantum circuit. Now I will assign now to this x0 the first value from the feature, the first data point. Now you see it with just a number there. Now I'm going to visualize this data set on the block sphere. And it looks like this. Now, if you look at this, you can tell from the beginning that if you measure along the Z basis, you will not have a good performance. Because look, so you would like to have all the blue ones. This should be from class 0. Okay, this corresponds to the ones at the North Pole. And the red ones, you would like them to be from the 1 class. So this should be more oriented to the South Pole. And if you measure along the z-axis, what do you have? So these ones that are above the equator, these will have a higher probability of being from state 0. The ones that are below the equator, these have a higher probability of being measured as the class 1. So now let's do that. So now this function, okay, so what this is doing is, so you pass it a circuit and it's going to create this, it's going to give it the parameters that you have, give it the values, run the experiments on the simulator, get the counts, and then compute the probabilities. So I'm gonna run this, and then I'm gonna use this function, and this is going to give me the probabilities for each one of the samples on your data. Okay, now you print here some numbers. And what I want to do is get the predictions, because now, based on these probabilities, I'm gonna say if each one of the samples corresponds to either class 0 or 1. And this is the part that, so comparing the probabilities for each one of the samples, this will give us the performance of the model. So I'm gonna run this one and the next one. So as you can see here, so what I have is a sequence of true and falses. It's true when we have a data sample classified correctly. So they have the actual label that we want. And it's false if not. So that's kind of bad. So if we compute the accuracy, so this is the percentage of good predictions that we have. I run it here, and you can say I have 35% accuracy. So I only write 35% of the times with this classifier. Now, if I plot this on the block sphere, now, and this is what we were expecting. So the ones with the dot, these are the ones that were correctly classified. And the ones with the X, these are not correctly classified. So as you can see, the ones that were red, that were supposed to be from class 1, that are above the equator, these are not classified correctly. And the ones that are blue, that are below the equator, these were not classified correctly. Okay. Now, what will happen if we rotate the qubit along the y-axis? So here along the y-axis, it depends on how much you rotate it, okay? But if you measure along the y-axis, you're measuring like the height along the y-axis. But it's the same for all the points because they lie on the equator with respect to the y-axis. So we know from the beginning that measuring along the y-axis will not work. So, but let's do it. So, and we know how to do it because we have equations for these gates. So we have equations for the X, Y, and Z gates. And we know that if we want to measure along the y-axis, we need to do a couple of rotations that are represented by this. So this, what we need to do is to each one of the states, we need to apply the Hadamard gate and this S-dagger gate. Now, I haven't told you what the S-dagger does. It doesn't really matter for now. It just helps us do this rotation to measure along the y-axis. So here what I'm gonna do is, okay, so I declare parameters, I create the quantum circuit, and then on top of that, I'm going to apply these H and S-dagger gates that will rotate the qubit along the y-axis. But what will happen when I compute probabilities? Look, almost all of them are 50-50. That's what we were expecting because all of them are on the equator along the y-axis. So this is not helpful for the classifier. Now, if I get the accuracy, this is 30% accuracy. That's not good. If I plot it on the block sphere, you can see that some of them are correctly classified, but most of them are not. So what do? We need to, okay, so looking at this sphere, we know that if we measure along the x-axis, then all the blue are on one side and all the red ones are on the other side. So if we have a way to measure along this x-axis, the classification will be done correctly. And to do that, we only need to apply an H gate there. So exercise. Okay, no, forget it. This is not an exercise. This is already solved. Sorry. So, okay, so if I run this, okay, so this is the data I want to classify. And what I will do is I'm going to apply an H gate so that I can measure along the x-axis. Now, again, this is technical, but it has to do with these C, X, and Y matrices. But we know how to do it. So if I do this, now I just apply an H on top of the feature embedding. Now this will allow us to rotate the qubit so that when we measure, we are actually measuring along the x-axis. And when I do this, look, I get 100% accuracy because I was measuring along the x-axis. Okay, now this is plotting all the correctly classified points as points, not x's. So in this case, I have a perfect accuracy. And that's because I was able to measure along the x-axis. Okay, so let's go back to the presentation. So we learned that we can measure, even though that the quantum computer only allows to measure on the z-axis, we can apply some gates, some rotation, so that we can measure along different axes. And the thing is that we don't always know in which axis is it's better to measure. And in order to do that, to fix that, what we do is we introduce some parameters on some gates. Now this W can be either X rotations or Y rotations or Z rotations. And we're going to run an optimization over this theta so that when we minimize the error, this will measure along the correct axis automatically. Okay, so this will learn the specific rotation we need to do specific for that data set. So now the classifier depends on the data X and the parameters theta. Yeah, so the optimal measurement is the one that minimizes the classification error. And now to train the classifier, what we need to do is we need to find the optimal theta. So yeah, so in this case, we have some theta, some values, and it's the same thing as when we do optimization. So we're on a landscape and we want to minimize the value of a cost function depending on the theta. So we need to vary this theta to obtain an optimal set of parameters. And we need an objective function. So for this, one example is just to see how many of them are correctly classified. That's one way to do it. So you just count how many were correctly classified with the classifier. In this case, this example, these were 2. Yeah, so the training, we do it only on the training set. At the end, we test it on the test set that we didn't use for the optimization. And we hope that this will behave good also on the test set. Okay, so now the algorithm, the learning algorithm looks like this. So you input your data set, your training data set, and your classifier. And inside you will have a loop. Now this theta 0, this is just an initialization of the parameters. This could be just random numbers. Then you need to compute your error on your data set with your loss function, your cost function. And then based on this, you can compute the gradient and do gradient descent on the parameters theta. And all of this, you can do it automatically on Qiskit, so you don't have to go and do the details. But the important thing here is that, so you run this cycle several times, and then you hope that you minimize the error for some parameters. That gives you a classifier that it's optimal for this data set. And this is what we call a hybrid loop, a quantum classical loop. So here, the part on the top, this runs on the quantum computer. So this, we put it the parameters, we put it the data, we send circuits, and we receive some probabilities from the quantum computer. We evaluate the loss function on the classical computer, on your own computer, and do the actualization of the parameters. Then with these new parameters, you create a new quantum circuit and keep on going. So this is what we call a quantum classical loop because it's running on the classical computer and the quantum computer on a cycle. So, and this is just a way to do it on Qiskit. Basically, you have your ansatz, which is the model, how you embed the data into a quantum state, and how you measure along different bases. And to train the model, you pass your circuit, your parameterized circuit with your parameters and your data to this thing that is called neural network classifier. This is a class on Qiskit. And you just do like the dot fit and pass your data. And this will run automatically this quantum classical loop. And I think we will have time to finish this. Okay, so let's go to the fourth notebook, and it's the same story. So I think you know how to do it. So upload the notebook. This is the fourth one. You need to upload also the utils. And pip install everything. So Qiskit machine learning. And wait for 45 seconds. Okay, now you go to runtime and restart runtime. And you should be good to go. Let's see if it's working. Okay, it's working for me. Is it working for everyone else? Yes? Okay, good. So, yeah, so first, okay, the imports is done. Now we get this QASM simulator. This is going to be run locally, again, not in the cloud. And we get the iris dataset. And okay, so here we need to build a parameterized quantum circuit. And we're gonna be using this that is called toLocal. So this has automatically, it has a way to embed the data and some parameters. So when we run this, what it's doing is you create parameters, you embed the data as angle embedding using this toLocal on top of that. So, okay, let me tell you what this is doing. So this angle embedding is applying these Rx rotations on each one of the qubits for each one of the features on your data. So each data sample will be plugged in here as angles. And these toLocal, this will train the measurement of the qubits. So the parameters inside this toLocal will allow us to rotate the qubits. Now, if I draw this decomposed, you will see what's inside these toLocal. So inside this toLocal, you have some RC, Rx rotations, and CNOTs. Now, this is longer because in the toLocals, I have repetitions equals 2. So I'm just putting that because I know that I already tried it, and this works good for the iris dataset. So, okay, now what we do here is we get some initial weights. So these are the initialization for the optimization. This is what we call the theta zero on this quantum classical loop. And we're going to be using this interpretation function. What we're going to do is we're going to measure each one of the qubits and look at the parity of the qubits. Okay. And this is what this function is doing. So you just get the number of counts for the one state. You do this %2. This will give you the parity. If it's the same parity, it will give you 0. If not, it will give you 1. Okay, now this quantum instance, basically it receives the backend that the simulator you're using, and some seeds. So the seeds, again, is to produce these probabilities, just to ensure that we all obtain the same things. This number of iterations is the number of times we run this classical quantum loop on the quantum simulator and the classical optimizer. The classical optimizer we will be using Scovilla. We have different choices. We can use almost any optimizer from SciPy. And now this is the class from Qiskit that we'll be using. So this circuit QNN receives, now QNN is short for quantum neural network. So the circuit is the one we already built. The input parameters, this is the data. So we know that this embedding circuit, we have the parameters, this is the data. These weight parameters, these are the trainable parameters. Now we take it from the ansatz, that the ansatz is the two local. And we give it the parameters of this. We give it an interpretation function to see if the data was correctly or not classified. And this is the parity function we just defined. The output shape should be the number of classes that we have. In this case, we have 2. And the quantum instance, which is how much the simulator in which you're running this. So once you do that, you can see that you can apply a prediction for this. So if you use this class circuit QNN dot forward and you pass the data here, so I'm passing the first data sample and the initial weights, this will produce a prediction in terms of probabilities. So as you can see, this one will be classified as class 0. Merci. So now, how do we train it? Now, once we build this circuit QNN, again, this circuit QNN has the data embedding and some rotations for the measurement. And when we do that, we pass it to this class neural network classifier from Qiskit. So the neural network will be this circuit QNN we already built. We need to pass it the optimizer and the initial point. And then we just do this circuit classifier.fit. This will produce the training. This will do the training. And you pass it the data that you use for the training. So the X train and the Y train. The Y train are the labels. Now it's done. So let's look at the accuracy. Now you can see this is not good. So this is 50-50, 50% accuracy on the train set and 50% accuracy on the test set. So, okay, now you can try to do one by yourselves. So here, you can choose either the CC feature map from the previous exercise or the poly feature map to do the data embedding. And you can use again the two locals as an answer. So the answers will be, in this case, the rotations before the measurement. So are there any questions so far?
Yeah.
Yeah, sure.
So trying to summarize, you have quantum features, so you have these circuits.
Yeah.
To the number of data.
Mm-hmm.
Top of that, you have a two local.
Yes.
So this is still the quantum feature, right?
Yeah.
Rotations.
Yeah, the two locals is the one that produces the rotations before the measurement.
But it's random format.
Is what?
When you start, it's completely.
Yeah, when you start, it's completely random. Yes.
Then you have on top of it circuit QNN.
Okay, so here. Okay, so first, you build this thing, so you have your data embedding, then these two local, which will be our rotation, and you build this circuit QNN here. So you need to pass it the quantum circuit. You need to pass it what are the parameters you use for the data? These are called the input parameters. So these are on your embedding circuit. And the weight parameters, these are the ones that you're gonna train.
So it's the term neural network. So the neural network would be. Yeah, the neural network.
No. No, it's confusing. I know. There's no neural network. Yeah, sorry.
So in fact, you try to learn parameters from the two.
Yes.
You have a cost function on that,
Mm-hmm.
and you have an optimizer.
Yes.
That's gonna run the gradient.
Yeah.
That's all.
Yes. Yeah, that's all. Yeah.
Why we call it a neural network?
I think because they were trying to copy TensorFlow. You just create one, and then you would like to have a method that is just dot fit, and does the training. This is how you do it in TensorFlow. In
Yeah.
PyTorch, it's a little bit more involved, but yeah. And they like to call these things quantum neural networks, although I don't see how that's a neural network. Yeah. So were you able to do it? No?
I did, I do have, I'm gonna fit the CC.
Uh-huh.
And I have a train and test secretary.
One?
Yeah.
Ah, good.
But I just tried to understand what I did.
Yeah, no,
So,
that's exactly the point. Like, okay, go ahead.
Your secret, you're having a more complex secret to like having different stuff or exploring different dimensions.
Mhm.
Where you just like operate many operations that hopefully will help to separate your private data.
Mhm. Yeah.
Since you're having some version of your qubits in a more complex way, right?
Yeah. Yeah, that's grosso modo. Yeah. You?
I got an error in part.
Ah, okay, let me.
You check the variable name. And
Okay, yes. So this thing returns a service. So if I use this feature material, it will. Yeah, but if you need to pass the parameters. So if you go here at the top, that parameter. Yeah, because yeah, so I need to see with that parameters. Yes. The one will be for your data and the other one. I think that should fix it. And also for the other one. Are you good? So, and stuff. Yeah. Sorry again. Okay, now it's working. Good, thank you. Anyone wants some help? No?
Yeah.
try to feature map, it's having it's not defined, so I'm trying to.
Oh.
Can I give them a term, like, I can either use CC feature map or.
In principle, I think you need to import it.
Okay.
Yeah. 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 Import boxes. Yeah.
So the CC feature map that compose and that's just for visualization.
Yeah.
It's working.
Okay.
Yeah, so I hope, yeah, we have a couple of more minutes. So I hope you can see that there are many things you can try. Some of them will be good, some of them will be really bad. Now, I know I told you that quantum machine learning is not working. and that's actually the case. But that also is good news for us, because if we try to do research and we come up with something new and we run it on a quantum computer, that's 100% publishable. So, so that's good. So, and I think that's what we want, right? We want more grants. We need papers published. It's better for the students too, if they have published papers. So also I've been doing research on my own on this, trying to scale it for bigger data sets. I can tell you what I've been doing. Maybe you can try it on bigger data sets. Have you tried have you looked at the MNIST data set?
Yes.
Yeah. Okay. Maybe we can start with something like that before going for big images like the ones you're using. Right now, there is no quantum classifier that works on MNIST. I've been trying to do it. I have a couple of ideas that we can start trying. The only thing I've been lacking is manpower. So apparently I have manpower now and women power too. So
Good idea. Yeah.
so for next Thursday, we can start discussing. I can present. Oh, you know what? How's the people from chemistry? Because I think there are people from chemistry and geomatic, but Nicolai's already gone. But okay, anyway, so I was I was gonna ask if we need a separate group for chemistry and another for geomatic, but I think we'll see that next week.
Yeah.
But yeah, we can start with some basics like. There are other things that can go wrong with quantum classifiers. And this is one of so you need to compute the gradient at some point to optimize these circuits. And there's one thing that when you add too many qubits, the gradient becomes zero, like completely zero. So that means you cannot run an optimization. Okay. So that's another thing we would like to solve. Also here, we only tried one type of optimizer. There are other types of optimizers that we can try. And so other thing we haven't looked at is how these things behave on a real quantum computer. We can try also like run these same things that we were running on simulators, try to run them on a real quantum computer so that you have a feeling of what's happening on a real quantum computer. It's going to be basically the same. You're just going to change one line of code. Instead of asking for a simulator, you're going to ask for a real backend. Yeah, so after that, we can start like looking at papers. Like this is not going to be high level, I promise you. You don't need to look at the details of quantum mechanics. All these operations we've been doing with the quantum states and equations and all of that, that's very complicated. That was just to give you a taste of what it is to do quantum. But for quantum machine learning, you don't really need to look at the details. Even more if we're going to use real quantum computers because of the noise. So because of the noise, we cannot keep track of the real quantum state. So you don't really need the mathematics behind all of this. So yeah, it's basically trying new things, run them in different ways. There are other ways we can try. We also have a mid-circuit measurement, so we can measure a qubit in the middle of the circuit. Apparently, that helps with this vanishing of the gradient. That's something I would like to try. So that's it. I don't know, for the next Thursday, do we have still 3 hours?
I think so, yes.
Yeah?
I'm not sure it's in the agenda.
No, the first was just the 3 workshops.
Yeah.
We need to schedule it.
Mhm.
Yeah, can do that.
Okay.
September.
Okay, so you're good for 3 hours every Thursday.
Yeah.
Sure, those students are going to be
Yeah.
available for the program for us to just the 3 workshops.
Uh-huh.
Like if they want to, like they can.
Mm-hmm.
But it's going to be like.
Yeah, I can manage it on my side.
Mm-hmm. Well, actually, since it's going to be like a reading group, like just discussion, I will not have like something prepared like for 3 hours. We can start with 1 hour, let's say, just to start discussing. Yeah, exactly. Mm-hmm.
Yeah.
Yeah, is there a question online? Any questions? Comments? Okay, so if that's the case, thank you all for coming, for sticking all the way to the end. That was very brave of you. And I guess we'll be doing more things in detail for next week. So see you next week.
Welcome.